take the double integral of x plus y over the region R, where R is the region bounded by these four lines. In order to do this integral without any fancy tricks, we would need to split it, either splitting it vertically and having one double integral for the left side and one for the right side, or splitting it horizontally and having one double integral for the top half and one for the bottom half. However, notice some symmetry with the setup. The yellow lines are parallel and so are the pink lines. The equations of the lines that make up the region might give us some additional clues. Moving all the variables to one side makes what we need to do even clearer. Let's assign u to equal y minus x and v to equal x plus y. That would make the bounds for the integral as follows. U goes from 0 to 1, and v goes from 2 to 3. While the bounds are now expressed in terms of u and v, we still have to get the integrand into this form, which involves a little bit of algebra. After evaluating the integral, we get that it's equal to 5 halves. So that's the answer, right? Wrong. 5 halves is not the answer to the original integral. In the previous video, we visualized the double integral as the accumulation of volume as a cross-sectional area sweeps back and forth. However, an equivalent way to view this is to break up the region of integration into many little squares and multiply the area of each square by the height, which is represented by the integrand, to get the volume of a little rectangular prism. Then the double integral is like adding up these volumes within the domain, taking the limit as the area of each square approaches 0. Now this brings us to an important point. When we perform a change of variables, we are now integrating in the UV plane. But are areas always preserved when shifting over? The answer is a definitive no. In this case, areas in the UV plane are twice as big as their corresponding areas in the XY plane. This scaling factor between the areas in these different planes is called the Jacobian, and you will frequently see this notation. The Jacobian can be thought of as the conversion factor we need to bring an area in the XY plane to the corresponding area in the UV plane. We will talk about how to compute this scaling factor a little later, but for our integral, this means that we are not accounting for the additional factor of 1/2 in the integrand. Thus, the integral in terms of u and v equals 5/4, so our original integral also equals 5/4. An important prerequisite we must discuss before the Jacobian is the 2D determinant. For any two vectors x and y, the determinant is an operation we do on the matrix containing x as its first column vector and y as its second. The determinant is the area of the parallelogram spanned by x and y. However, this comes with one important qualification. The determinant can be negative depending on the orientation of the vectors relative to each other. In the UV space in which we are integrating, let du represent a little nudge in the pure u direction. To take this nudge back to the xy plane, we have to perform a transformation, which is approximately linear on the infinitesimal scale. And the same goes for a little nudge in the v direction. It turns out that the transformation of du has the components, the partial derivative of x with respect to u, and the partial derivative of y with respect to u. Some intuition for this is that if x changes a lot with a little change in u, this change will be reflected in the partial derivative. The exact same can be said for the y-coordinate as well. Similarly, the transformation of the little step in the v direction can be written as the partial derivative of x with respect to v as the first component, and the partial derivative of y with respect to v as the second. Finally, in order to find a little area element that the transformation produces, we must take the determinant. Actually, there's one caveat. We take the absolute value of the determinant because we don't care about the orientation. We only care about how areas scale. Now, I hope you walked away from this video with a deeper understanding of what the Jacobian really is. It's a scaling factor that we must include whenever we perform a change of variables to account for the fact that areas within these different domains are not the same.